Yeah, so I'm back. For those of you who weren't here this morning, I'm Eric. I'm from Timescale. I'm a core database engineer. And in this talk, I want to talk more about TimescaleDB and how we can use it together with Prometheus and Grafana for storing and analyzing and visualizing metrics. So again, this is something I talked a little bit about in the last talk, but why use Postgres for this kind of stuff? Well, again, it's reliable, familiar, you get full ACID support, all the tooling around it. You get SQL, the powerful query language. You have joins, you can combine different types of data, time series with metadata or other types of business data. And again, you can simplify your stack, stick to one database instead of having your data split across many different databases. So that's where TimescaleDB comes in. It's basically Postgres for time series data. So when we set out to kind of build TimescaleDB, there were a couple of common complaints that we wanted to address. So we heard a lot that Postgres is hard or almost impossible to scale to this type of workload. People sometimes complain that, oh, I have to define a schema. I happen to be in the camp where I actually think schemas are a good idea, but I totally see that for some use cases, it's very convenient to just be able to throw data into your database. Other people say, as we've heard, that SQL is complex and has poor support for querying time series data. If you want to delete data, so typically you have with time series some kind of data retention. In Postgres, it's very expensive to delete huge amounts of data because it incurs some vacuuming. This is basically a garbage collection process to delete the old data once it's deleted, because Postgres itself doesn't actually delete the data when you do a delete. And finally, people say, like, well, I can't use TimescaleDB or Postgres with Grafana, so why should I use a database that I can't use with Grafana? Well, I'm going to claim today that most of these problems, if not all, have been solved in one way or another. If you combine Prometheus with TimescaleDB and use Grafana as the visualization. So now we have something that scales for time series workloads. And I'm going to talk more about how we actually scale Postgres to this type of workload. You get more or less automatic schema creation, and that's actually something we've done specifically for this use case. So there's another Postgres extension that we've implemented called PG Prometheus that helps out with this, and I'm also going to talk more about that later. So now you have something where you have basically advanced analytics with full SQL support, and we've done time-oriented optimizations for SQL. You have like extra functions that you can call to group by time, etc. And you can by actually leveraging the kind of partitioning we're doing to get the kind of scale that we're talking about, you can actually drop data very easily by just dropping subtables. And that doesn't really incur much vacuuming at all. So it's very efficient. And now we have Grafana support via either the Prometheus connector, you can use PromQL, or you can use the new Postgres data source since version 4.6. And I want to give a shout out here to Sven Klem, who's the guy who actually implemented this data source. So how does all of this stuff work together? Well, first you need a way to collect your metrics, and this is where Prometheus comes in. So, I mean, there's been a lot of talk about Prometheus. It's on the rise in terms of popularity. It's not only a data store for time series, it's actually a set of tools for doing monitoring in general. So it has this way to collect metrics. It has this kind of pool-based approach where you're scraping remote endpoints for data from various sources. And then it has PromQL, which you can use in Grafana to query Prometheus for time series and visualize. One thing that Prometheus doesn't do very well, however, is long-term data storage. And that's something that the Prometheus people actually thought about. So they implemented something called the Remote Storage API, and that's what we're using to hook things up with TimescaleDB. For that to happen, we had to implement two things. One is an adapter, which is basically a translation layer that kind of speaks the remote storage API on one end and the Postgres protocol on the other end. And then you need some conversion to kind of map the Prometheus data model to how you actually store things in the database, some type of schema. We choose to actually implement that in the database rather than the adapter, because then it can be reused by other tools that want to speak kind of Prometheus to the database. So I'm going to talk more about that. I'm not going to talk much about the adapter because it's just a simple translation layer. First, however, I want to talk a little bit about how we actually scale TimescaleDB to handle this type of workload. So here's a scenario. You have sensors deployed in various buildings. They take temperature, humidity readings, whatever, and you have this data coming into your system over time, right? So what we do in TimescaleDB is that we do something we call time-space partitioning, and this is for scalability. So the first thing we do is to slice the data up in the time dimension. But then you can also optionally add additional dimensions, for example, a space dimension. So imagine that you partition by your device or sensor ID or something. And I think this is the most common approach to how you partition in TimescaleDB, but you can actually add any number of dimensions. So what you end up with in the end is something we call a chunk. This is a kind of a multi-dimensional partition. And this is actually just a subtable in kind of Postgres inheritance structure that's been around for some time. But to make this easy, we built what we call the hypertable abstraction around all of this partitioning to kind of hide for the user what's going on underneath the hood, to make things really simple to use and give the kind of impression that you're actually working with a regular Postgres table. So we worked a lot on adding support for things like triggers and constraints, indexes, even unique indexes with some restrictions, things like upserts, these on-conflict do something statements, and a lot of table management stuff, because this doesn't like work out of the box in a partition table. So you basically have to do all of these operations manually on subtables, etc., and manage this. And then we have kind of an insert engine which takes care of the space-time partitioning. So when you have tuples or data values coming into your system, it automatically kind of routes this to the right partition, and if there's no partition or chunk that exists for that particular time interval or multidimensional partition, the engine will automatically create that for you. It's actually pretty easy to get started if you're coming from the Postgres world. So the first thing you do is just define your table schema. You have a time, maybe temperature, humidity, some device. You can have any number of columns. And then you set up your hypertable, basically converting this table into a hypertable by one function call, where you'd give the table name, your partitioning columns, time, device, and how many partitions you want to create per time interval. So in this case, 4 partitions per time interval, which is 1 week. And then you're just ready to insert data as you would in any table. So in this case, it would create one chunk from this insert statement, and then you're ready to query. And it just works like a regular table. If you want to repartition, it's also simple. You just set another time interval, or you set another number of partitions. And this will apply to any sort of uncreated chunks. The existing chunks in the system will remain partitioned the way they were when they were created. So this will only apply to future chunks. But if you have this kind of retention window, eventually you will kind of phase out the old partitioning scheme. So some of you might ask, well, there's this new thing in Postgres 10 called declarative partitioning. It's supposedly very nice to work with. But if you want to achieve the same thing with Postgres 10 partitioning, this is what you have to do. And this only sets up the first couple of chunks for the first time interval. So every time you need to write to a new chunk or partition in this case, you have to do a set of these table commands again. And don't ask me about repartitioning. So what kind of performance can you expect? So here we're comparing to regular Postgres. So we can sustain up to 140K metrics per second using a batch size of 1. So this is like a single row insert statement. And you can see that as the number of rows in the table grows to maybe 50 million rows or so, then suddenly, all of a sudden, Postgres is starting to struggle. And eventually, you have lots of variance and poor performance. And the reason is that eventually indexes become too big for Postgres to be able to keep them in memory. And because you kind of write to random places in an index, it needs to swap things in and out of memory. By doing the kind of chunking we're doing in TimescaleDB automatically, you can kind of right-size your chunk to always fit within memory. And we always keep kind of the most recent chunks warm in memory, so you're kind of continuously writing, typically using this workload to the same chunk all the time. You can scale performance even further if you do batching. So this is a batch size of 10,000. And then you can do over 1 million metrics per second. So this is like 10 metrics per row. And this is different from like Prometheus and maybe Influx, because they typically don't have like a row-oriented data model, so they typically insert 1 metric per statement. So here you see that we've scaled in this benchmark the database to 1 billion rows, and then we have like a more than 20x performance improvement over regular Postgres. Okay, so again, Postgres 10. Postgres 10, in theory, should be able to achieve a similar performance, but they're doing things a little bit weird in Postgres because it's not really designed to handle a lot of chunks or subtables. Maybe it's more designed for traditional sharding. Maybe you have 10 partitions or 100 maybe. And the reason why we see this really poor performance is that every time you're doing an insert, they're opening all the subtables. So you're taking a lock on all the subtables, you're doing every work you need to do on these subtables just to insert into one of these subtables. So if you have thousands of subtables, it's going to be a huge cost. So what you see here is that with the number of partitions, as the number of partitions grow, then the insert rate really, really goes down, while in TimescaleDB, we're only opening the chunks that you are actually writing to, so we're pretty much constant there. On the query side of things, you can also expect performance speedups because we're doing this kind of partitioning, so you can do constraint exclusion to exclude chunks from queries, and we're also adding new optimizations to the query planner. So for simple column rollups, you can expect up to 20% performance improvement, group bys up to 200. Time order group bys, we're doing special optimizations on like using the proper time index for these queries that the regular planner cannot figure out, so we can see up to 10,000x performance improvement over regular Postgres. And for deletes, by just dropping old chunks instead of doing deletes in tables, you can get up to 2,000x performance improvement. So how do we actually store data in the database if we look at this particular scenario we're talking about? We're doing metrics, we're using Prometheus to collect metrics, etc. So that's where PG Prometheus comes in. So what we did was to sort of implement the Prometheus data model within the database to make it really simple to insert data, and you don't have to really care as a user how that data is actually stored within the database. So the first thing you do is you just create a table using this new data type, which is called prom sample, which represents a Prometheus sample. And then you can insert metrics into this table using the familiar kind of Prometheus format that you will see if you scrape a Prometheus endpoint. And this creates then this data type internally and stores it in a column. You can even do funky things like scraping manually endpoints by doing curl and then piping the result into the database. So you don't even need Prometheus to collect metrics. You can also query raw samples. So you just query the table and you get back whatever you inserted. But this is not just a string stored. It's just the representation of the data type. Internally, it's stored in its component parts. So you can separate that out, so you get separate columns for time, name, value, and the labels, which here is returned as a JSON-B. You can also normalize the data storage. So in this extension, you can do a function call to set up your metrics table, and that will kind of split the storage into separate tables for your values and your labels. And it will set up proper indexes, and it will add a convenience view for inserting and querying the data with these columns. So you get basically the raw sample and sort of the individual component parts. You can easily query this view with a query that looks like this. You want to get the last 10 minutes worth of data from the CPU usage time series, and you query the labels using the standard JSONB query thing that already exists in Postgres. So now you can, with the new Postgres data source, you can hook this up to Grafana. So with this system, you can either query Prometheus to get your metrics, and Prometheus here works more like a cache. If it doesn't have the information cached in its own data source, it will fetch it from TimescaleDB and then store it in Prometheus and return the result. But you can also query TimescaleDB directly using the new Postgres data source. So here, for example, we're visualizing the CPU metrics, and this is what a query actually looks like. So obviously, if you're used to PromQL, for example, this is obviously a lot more verbose or complex, but it's also more powerful. And this is pretty early days in terms of what this data source can do. I know that a better query editor is being worked on, so in the future it's probably going to be much, much easier to kind of explore what kind of time series or data exists in the database and sort of generate a lot of these queries automatically. You can also do things like set up variables if you're doing templating. So if you want to query sort of in this normalized data schema, you can query the labels table for all the distinct values for example, getting a list of hosts in the system, and then you can use this for templating. So this is pretty much everything I have to say about how we have been using Prometheus and TimescaleDB and Grafana together. So if you're interested in learning more, you can join our Slack if you want to. There's a web page you can go to log in. You can check out these open source projects on GitHub, TimescaleDB itself, the PG Prometheus data type, and the Prometheus Postgres adapter. We also have like Docker images and stuff to easily set this up and run in your own system. Yeah, that's it.
Thanks so much, Eric. I think we have time for a question or two, if anyone has one. Yep. Question from Andrew.
So I kind of have two questions. One is, what sort of, is there any sort of performance hit using the PromQL adapter? Like, how intelligent is the query planner and with the API request from Prometheus as far as optimizing stuff? And then the other is, when you do a delete, do you still vacuum on a subtable if you like set an edge that's in the middle of a subtable, or is it just delete to the nearest subtable?
So yeah, let's answer the first question. I can't say actually that much about the performance hit because this is kind of a hobby project in some sense, and I haven't like extensively explored what the performance hit is if you actually have to hit the TimescaleDB database to fetch things, but I've never seen it being a real issue when I've played around with it in Grafana. I mean, as I said, we're using kind of Prometheus as a cache here, so it's like, if the cache is warm, it's going to be as if you were querying Prometheus. Otherwise, it's obviously going to take a little bit longer time to kind of fill that cache. The second question was the deletes,
so when
right?
you do a delete, you do a delete, does it delete at the nearest subtable edge, or will it still vacuum a subtable if you give it an edge that's in the middle of one?
Yeah, currently we're not like doing anything specifically for deletes. So if you're doing a delete, you're gonna have vacuuming. But we kind of recommend that you kind of drop at the chunk level using our functions for dropping data.
Okay, so the function does it just at the drop level.
Yeah, exactly. So if you give some like horizon, you want to drop data beyond this horizon, it's actually going to figure out that, you know, even if that horizon lies within a chunk, you don't want to drop that chunk because it still has data that's valid. So it's just going to drop the chunks beyond that.
Cool. I think we have time for one more. If anyone else has a question for Eric. Yep. Oops, sorry. Where was that arm? There we go, from Ryan.
Is there anything like support for rollups? Like,
yeah, that's a common question we get. Right now, we're kind of relying on the fact that we're using Postgres, so you can like implement your own user-defined functions to do this stuff. You can use triggers on inserts to like insert into another table and then do some roll-up there. Or you can have a cron job in the background that's just doing a query on the table and then sort of saving it in another table and then dropping the old data in the other table. That said, we're actually working on more like first-class support for that kind of stuff because that's a common question we get. So, you know, sometime in a couple of months or so, probably, we're going to have something that's more kind of native that makes it easier to set this up. But you can do it already today with the existing functionality.
Cool. Well, thanks so much, Eric. Timescale looks like a really promising new time series database. Cheers.